the evening section or afternoon session. Okay, now we have Aida Maharaj, and she will talk about the algebras with symmetries in infinite setting. So Aida will continue with her topic, but in the tutorial. It's a tutorial session, right?
Yes.
Okay,
Hi.
that's great. Hello.
Hello again. So I hope you have had a very good, productive day. So, kind of tutorial, in my understanding, is supposed to be like exercises and problem sets. I hope you all have access now to some, as I said, some code to compute ideals of hierarchical models, and you have the PDF file that contains some problem sets. So let me okay. So so you have this here, and yeah. So my plan is so I have set some problems here in tutorial 1. I've set some problems that I'll kind of discuss with you what the problem is asking and give some hints on how to solve them. And I'm hoping that some of you do try them out and give me answers even after this session. Yeah, so the first problem I did mention yesterday a little bit. Maybe yeah. So the first problem is I think it's just a nice problem. That's why I said if you one
So
of
it
the
will be it will be generated by the sim orbit of x1 and node.
yes,
X1
and
raised to power and node. Yes.
yes, and yeah, one of the references I gave already gave the answer. If you unfortunately I did give also the answer here. It's in this example. So yeah, this problem is considered the ideal generated by so generators are of the form x1 to the n plus so on plus xn to the n for each n greater or equal to some n 0. And so there are infinite, and all the kind of the sims of these generators. So there are infinitely many generators up to sim, because for every n we have one. But this ideal lives in the polynomial ring R of x n, which we said in the other time, if we have an ideal that is sim invariant there, then it must have a finite generating set. So we know already by the theorem we said the other time, this one, when c is equal to 1, that our ideal is finally generated up to sim, and the answer in this case is going to be yes. It's going to be this will be generated by just x1 to the n0 up to sim. And yeah, give me 1 second because okay, it's all good. Okay, and the problem 18 is to kind of have hands-on on the lecture 2 I gave yesterday on these hierarchical models. And so we have we fix some simplicial complex delta, and here we are taking ground set 3, so just on the vertex set 1 to 3, and we let the ideal for the hierarchical model to be with delta and R1, R2, R3. So IR to be the ideal for this one, and I ask that we compute some of these ideals and see what happens. What happens with the generators? Do we have finiteness? Do we not? And maybe some idea how to use this. So how many of you have Macaulay tool downloaded?
We
Some
are
of the-
using the online version.
At the moment, no.
Great. No, it's all good. So if we go to the online version, so how do I new share? Share. So if we go here and you can copy what I sent. And if you have trouble reading it because it's an M2 file, you can open it as a Word file and you can just copy paste the code as like a Word code and put it here. So this is the code I sent. Okay. So yeah, so basically, yeah, you may have more than you need here, but you have everything you need at least. And yeah, so once you do that, the idea is that you plug in the vector r, and so yeah, once we run what I said, we plug in r, the vector of states. We plug it in as right now it's written that r is inputted as a set, but an order matters. So r1, r2, r3. And the facets, now something to kind of make point out is that the counting usually when coding starts from 0. So we don't have vertices 1, 2, 3, we have 0, 1, 2. So for the example, yeah, so the first example is going to be like this, 0, 1, 1, 2. And okay. And then what do we need from here? We need to compute, we said, the just to make the computations faster. In fact, we have oh, we already have written this. Okay, so yeah, so we have this our ring. I called it probability ring here just because it came from statistics, the word probability. But so we have the polynomial ring. This is our what we called where are we? This is like our R of X. In this case, it's going to be, yeah, XR, like this. And here, this is the ideal that we said, I of R. So R needs only this like vector R. And the ideal needs the vector R, the facets, and just we put also this polynomial ring to kind of point out to Macaulay too that this is the ring we want to work over, because otherwise it creates a new one, even though it's identical, and sometimes it creates problems. Okay, so this was our ideal, and in order now to see the ideal, I prepared to write a list of icons of this one, because this just gives the list of the generators, I think, as a table, and so I like that one. So in this case, for instance, when we had here 2, 3, 3, we got, yeah, these generators. Yeah, when we worked together, these were called X, IJK. Here they are PIJKs, but okay.
This is a single generator, or each row
No, there are
represent
these are each of them is a generator. These are all binomials because this is a monomial map, what we described. So all of them are binomials, and each line is a generator. So maybe we can try something smaller. So if we take R to be what I said, no, 2, 2, 2. And then we ask again, yeah, so we are dot R. And then we ask I to be, what do we call it here? Okay, so yeah, or you can see it this way. So this is the ideal. It has two generators, or I prefer usually, as I said, not least of I like this because this just sets the two generators. It puts them in a table, so I prefer I read them more easy. So when we had 2 to 2, we had these two generators. And then if we change, so let's say we have, yeah, R equal to 2.3. And again, and then we have I. So yeah, and let's compare what happened from here to here. This is not that big. How do this work? Yes. So this was what we had earlier. This is what we had in the second step. So what happens if we compare these two? What do you see? Do you see that this second one is it's the ideal of O in O25 is included in the ideal O24?
Yes.
Yeah, so this generator here is the same as this one here. And this generator here should be this one here. But you have others, you have more. So what happens with this one, for instance, the new one here? You see that this one is obtained by just the one before, where you apply the symmetry action, like the permutation that sends 2 to 3 in the last index. You see? And similarly for the rest, I claim that you can get any other new generator that you see in this table by these two here. Does that make sense? Is that clear? If it's not, yeah, it's okay. We say it's not.
Yes, it's fine.
Okay. Okay, and yeah, so that's kind of what it is supposed to happen in I hope this is the problem set. Yeah, so this is what's supposed to happen in problem 18. And yeah, so for facets 1, 2, 2, 3, and then you try for this facet set 1, 2, 2, 3, 1, 3. And I claim, so this was like the triangle thing. It was the no three-way interaction model. So I claim that when you only let the last index vary, then you do have some stabilization phenomena. You do have some finiteness up to symmetry in part B. And we can like see what happens. So if we take facets here, so change. So if we take 0, 1, we said 1, 2.
You cannot see your screen.
Oh, thank you. I should maybe have just shared all my desktop and okay. Okay. So yeah, 1, 2, 0, 1, 1, 2, 0, 0.2. You can see now. Oh, what did I do here? To protect global. Okay, I'm gonna have to reset it.
You should start with capital F.
Oh, really? No, I don't think the name matters. I think it's just because I had already called it and it was not happy. I don't know. Okay, or maybe I should have. Sorry, maybe I should have. Okay, so let's start again. So R, let's take R to be 2 to 2. And we said that, yeah, you're right. I should have called them. Now I see I called them. But no, here it does not. Oh, okay. Because how do you add that? Okay. Okay, and we have okay, so in this case, we have our ideal is generated by one generator of degree 4, one binomial of degree 4. So let's say that we are changing, I'm gonna just copy all this. Let's say that we're changing and so let's say I take 2 to 3 and the same thing. So now we have 3 generators, but each of them is of degree 4, so that's not bad. So at least we do see that the degree is not increasing. So when the degree does not get higher, like when we don't require generators of higher degree, that's good news. And then let's take this to be 2, 4 and see what happens. Okay. Now again, the degree did not get higher, so it's still 4. And you can also try for 2 to 5 if you want, and so on. So degree does not get higher, and you can like really see that all the generators can be obtained by one of them, by the one with ones and twos. Yes. So this one, up to symmetry, produces all the others. Okay. But then if we change something, so if you go to the third problem, so we had 2, 2, 2, to recall this, how it looked. At this one, and then if we go to 2, 3, 3, then oh, that seems more scary. So now we require generators of degree 6. And I don't know how fast here this is online, but if we go with 4, yeah, then we will require generators of degree 8. And yeah, the kind of the guess is that maybe, oh, I asked the same thing. So if we go with 5, we will ask for generators of degree 10 and so on. I don't know if this is going to end because like you see that the number of generators grows quite a lot when we increase these states. Okay, so that's, yeah, I think it's gonna take time there. So, okay, and you share. So yeah, so that's about this. So here we have stabilization, here we have stabilization, here we do not have stabilization. And then problem 19. So this is kind of in service or like in this part 19 tries to combine what you heard Carlos talking about, if I'm not wrong, about maximum. Did you, Carlos, talk about maximum likelihood estimation in degrees?
Not yet.
Not yet. Okay, so this is like to combine with what Carlos will talk about. So maybe this is for like future one of these days. So one thing, this is a problem I would love personally, like to also think in the future, but it's Carlos will talk about this notion of degree, maximum likelihood degree, maximum likelihood estimation, and the basically problem 19 says what are possible contributions of this invariant theory of this asymptotic phenomena into likelihood geometry. So one thing is that this maximum likelihood degree, which you will learn soon, is unfortunately it's not invariant. It does not stabilize when the chain stabilizes, but most likely the maximum likelihood estimate can be handled, like it, with like this symmetry, for instance, can be useful in explicit computations.
So Aida, do you mean that this is like an unbounded sequence, like the ML degree just grows?
Yeah, no, I mean, for instance, the ML degree, when we have the independence model with varying number of states, ML degree is 1 all the time. So
Yeah.
one would think that maybe it does stabilize. But then when you take the, let's say, the no three-way interaction model, that's why I put this B here, where like only one of these states goes to infinity, then the formula for the ML degree is like something you conjectured, and with Taylor we proved. It's like something that goes to infinity is 2 to the m minus, or 2 to the n minus 1. So
Right.
it definitely does not stabilize. So ML degree does not seem to kind of, have that word stabilization. But the ML like estimator itself may have, like, one can use the symmetry to predict the ML estimate.
Okay.
I'm hopeful. That's all. So I think there are things happening, possible things happening for B.
Okay, that's very interesting. Thank you.
Okay, so that's and problem 20. So this kind of takes another turn. So we talked a lot. All what we talked was about symmetric group actions, but the actions does not need to be symmetric group actions. They can be actions by, I called something ink. If you see the references I sent, they talk a lot about this ink invariant, or they can be invariant under the general linear group. Or they don't need to even be, you don't even need to have a group. You can have something that like makes your object look finite. And that's something, maybe something silly, like in this example, maybe like some shift operator. So if we consider, so in this moment we are working with algebras, monomial algebras. So if we consider the poly, so the, so we consider the polynomial ring K is a field here of Xn. Then the algebras generated by xi squared, xi plus 1. These algebras are not finitely generated because for each I there are 2 generators, but we can think of them as like finite, generated by x1 square and x1 x2, and up to like shifting the indices altogether. So and that is not a, this shift operator is not a, it's not a group action. You cannot reverse it every time and stuff like that, but it does do the work that it gives a finite presentation. And now something that I missed saying the other time, so because I did not want to go into proofs as they are long and require time, but when I spoke about the independent set theorem, I forgot where it is. Yeah, oh, it's here. Oh, this is not the last version. Okay, so the independence, oh, this is supposed to be, here below this. Okay, so the independent set theorem was proven, the kind of the main meat of the theorem was that we had a monomial map coming from these hierarchical models. And when we have the independent set theorem being satisfied, then the image of this map lives in a polynomial ring of the form that we said is of this form. And hence one can use for the image, can use something similar to theorem 6. And then also one proves that the quotient is also finite up to symmetry, and these two make for the ideal, the kernel, to be finitely generated up to symmetry. That's kind of the core of that proof, but each of those parts require a lot of work. But like going to the image and looking at, like, because the kernel and the as an ideal and the image of a map as an algebra share a lot in common. So this sets us to, like, the kind of motivates us to work with algebras, and in particular monomial algebras. So that's why we are in this problem 10 and we are giving algebras. So so algebra means we have some generators, and the elements in an algebra are kind of these generators. And we can think of this as a vector space where the vectors are the generators. So it's like any any multiple of this is there, and any linear combination is there also, but not multiple by like an element in the ring. Okay, so now given an algebra, one can always create a monomial map, a map. So these are monomial algebras, a monomial map, where for instance, in this case, it's like the map. So we have two generators here, I goes to infinity. We create, for the first one, this map from x 2 times n to k of xn, such that x1j goes to xj square and x2j goes to xj plus 1. So the image of this map is exactly our algebra. And the question is, let's look at the kernel. Is the kernel finitely generated? So for the independent set theorem, for like work for the symmetry kind of version, the kernel is often finite. And there is work by Drysma and Egermons. Let me find it here. Where is it? Yeah, so this one, there is this work where they conjecture that for the sim case, always the kernel is finitely generated. They prove instances, but still it's a conjecture that the kernel is finitely generated. So my my question here is, look at the kernel of this map. So again, write some code with Macaulay 2. I do have some code already. If you want, I can share, but I thought maybe this is good to write down, try to write down maps for like fixed smaller n, like finite values of n, and look at how the kernels look like. Do you see any finiteness up to this shift operator? And my claim is that in these two first cases, you do see finiteness. The generators are of degree 2, very nice generators of degree 2. Okay, nice. They're nice. They're okay. Generators of degree 2, binomials. So we do have finiteness in the first case. Prove it. And in part B is you make a small change. You take this algebra generated by xi plus 1, xi plus 2. Similarly, you create this monomial map. And now the funny part is that, like, there is such a little change from here to here, but a huge difference in like asymptotic behavior, because now the kernel of the map here is not finally generated up to the shift. It's invariant, but it's not finitely generated, and it has a very non-trivial, with a lot of combinatorics, generating set. But it requires generators of high degree, of any degree. So, and it so that's, but again, this is like trying out examples and seeing patterns and seeing where we are going. And then lastly is like, so I gave some examples here. How do we generalize these examples? So maybe how do we write maybe a general problem inspired by these examples, a general class. Do we have a question? Also, does everyone know how to write down a map in Macaulay 2?
Maybe it is better to give an example, quick example, to just.
Yeah. So, for instance, if I were to, let's say I have this polynomial ring R Q Q. Oh, I need to share. How do I forget again? Yes. So yeah, if I have let's start. I have this polynomial ring. Let me start up. Okay. So I take the first target polynomial ring QQ of, let's say I have X 1 1 and tilde to X, let's say 2 2. Okay, so you can see again of R are these ones. And then, so I have 4 variables here. And let's say I'm taking as the target polynomial ring, QQ, of, I'm going to call them X1 tilde to, oh yeah, X1, X3. Okay, so X1, X2, X3. Maybe I should have started with 0 here. I should have started with 0. And then we can write, I'm going to write, okay, so I'm going to write a list where I want, so I want x11 to go to where, let's say I want x11 to go to x, comma 0, and star x, comma 0. So and then I want x12 to go to x, comma 0, x, comma 1. Oh, let's start here. And I want x21 to go to x, comma oh yeah, x12. I said I wanted this to x1, x1, x21 to go to x0, x, comma 1. Start here, and x, comma 0. What else do we have?
1 star x0.
X0, x1, x
1.
x1, x2. Yeah, I think, yeah.
0.
And let's say we have this one. I should have called this x2 then here, but okay. So let's see what happens, and then we create the map. So first we put the target, and then we put the, sorry, this, yeah, and then the source, and then we map image, and this is a map, and then we ask for the kernel of I, and it gives us one generator. For instance, in this case, in this case, it's generated by this one here. And we can call this if we want with I equal to, okay. And similarly, we can go to the next step where we, I did not need this 3 here, but okay. The next step is when we define R, we can go to 2, 3. And so and then we do the same thing. So we define the target, the source, where each element, with each of these variables gets mapped by our polynomial ring, polynomial map, and then we write down exactly what I wrote here. Okay, so that's how one would go for. How do I? Oh yeah. Yes. So this is how one would go for solving problem 20. So write down for different smaller, like finite ends, and increase this n with each step and see what is happening. But for extending results, maybe extending this. So I kind of give a hint here: xi plus 2, xi maybe tilde to xi plus c. Can we have a similar result for as long as xi square is there? And if we take like generators of degree 2, this is always like the kernel is finite. So maybe this makes a difference. So like kind of conjectures out there. I don't know. So, but this is an open question. And lastly, this is something also that I find very interesting, is so there is this notion of stage 3 models they are very similar to hierarchical models, but they are more general. So they are defined. So we said that hierarchical models are for determining relationships among random variables. Each vertex represents a random variable, and stage 3 models are to model the dependency among events. They are even more detailed, but one can assume that this number of events goes to infinity. And the question here is which stage 3s have, so a stage 3 has also an ideal associated to it with a nice kind of recipe on how to go to the ideal. I'll give one example. But not all of them are invariant under SIM. So first is to classify which of them have ideals that are invariant under SIM or under some other group action, but SIM works for many of them. And when they are, so what are some finiteness results or asymptotic results we can get about these stage 3s? And for this also there is a code already that my collaborators and I have shared on how to compute the ideals of these stage 3 models easy, so you don't need to start from scratch at all. So that's it. And lastly, so in this survey of where is this survey? Yes, this one. So they share some other problems more in concerning regularity, dimension, degree of filtrations of ideals. So if you want more commutative algebra kind of questions, you can find some of them here. Yes. So these are problems I'm proposing. So maybe I'll ask you, what is a problem that some of you find more interesting? You can create groups and work on them. And I can give more hints or suggest more on each of them. So while I'm doing that. Okay. Okay, so while we do that, I will give you an example of a stage 3 model, kind of to give the hint on like how natural this symmetry group action applies and how natural these stage 3 models are. So give me 1 second. Okay. So sharing. Um, Okay, so stage 3 models are, we start with the rooted directed tree. Just to say something like this. Okay. And we can put colors to the vertices, non-leaf vertices, and we also put parameters in each edge. So we have here theta 1, theta 2, tau 1, or maybe I should have just called them x's and y's to make it more. So x1, x2, y1, y2. And now whenever two vertices have the same color, their direct outgoing edges will have will share the same labels. So here I will have to have y1 and y2. And then the outputs are, okay, so I have P1 here to be x1, y1, P2 to be x1, y2. So I'm multiplying along the, from a root to the leaf, the labels. So the same here, and the same here, and the same here. So P3 will be x2, y1, and P4 will be x2, y2. And so the the map in this case will be from R of P1, P2, P3, P4 to R of x1, x2, y1, y2, such that as we have there, P1 goes to x1, y1, and so on. P4 goes to x2, y2. And this is our P, and the kernel of Phi is, in this case, if you check, is P1, P4 minus P2, P3. Okay, so the definition is take a rooted tree, put colors on the vertices, but keep in mind that two vertices have the same color. Only if they have the same number of, we can only put two vertices, set two vertices to have the same color if they have the same number of outgoing edges, and then those outgoing edges will have the same label. That's kind of the rule right now. I will not talk about the sum to one conditions here. I think this is perfectly fine for starting this problem. And now how do we go to symmetry? So I wrote them this way because that's how they usually show up, but one can do something silly. And I'm going to call this, the first one as P11, P12, P21, P22. And this seems now something we have seen before. And from this example, we can go to another one where we take these three again. And what we do is we had these two vertices, and maybe this time we have three of them. Okay. Okay, so then we have x1, x2, y1, y2, y3, y1, y2, y3, and then we have P11, P12, P13, which is the product of each, P21, P22, P23, and we similarly create the phi the same way, and the kernel of phi I claim is the ideal of the 2 by 2 minors of the matrix P11, P21, P12, P22, P13, P23. So and so yeah, so when we go to like add another one and another one of this, like, so that means that those events have more and more, maybe I did not tell you kind of the where do these things come from. So they tell about, yeah, each vertex represents an event, and the number of outgoing edges from that vertex represents the number of possible like next steps after that event. For instance, one place where this model here appears is like in independence, as independence model, saying that, for instance, that ability to do math is independent on, let's say, if someone likes poetry, so then these x1, x2 are the probabilities for liking math, and y1, y2 are probabilities for liking poetry. And so to say that these are independent means that, so independent on whether I like math or not, these like my preference for liking poetry is the same. That's why these are the same entries. So kind of this is like one explanation of this model, but like the stage 3 models are very, very general. So there may be many storylines that can be put on a stage 3. But that's kind of the hint on like how you see the symmetry showing up, like in this example. But you can do this over any tree with that kind of with that recipe that I gave. And so when is the symmetry group action useful, and when it is useful, so what is its contribution? Okay. Do we have any questions?
So good.
Okay. Yeah, so that's, yeah, and for this one, you do have already code where you just, and in fact, we have a math repo where like it's very kind of, there are steps that explain in detail how the input in a code should be, and how it should be interpreted.
So Aida, maybe people don't know what a math repo is. Maybe you can tell us about it if you want.
No, I can. I don't work with math repo, but so it's a place where usually people choose to add papers with code associated to their papers to keep kind of a system, like to do a systematic way of keeping useful information about papers. And maybe Carlos, because he's in Germany, can tell you more and give you a better explanation on math repo. honestly. So
Oh, you're the one who mentioned you have a math repo.
it's a math repo means that there is a website where we have shared the code with details, and I can just open that. Where did I? Oh, I'm sharing. Where am I sharing now? That's why I got confused. Oh, okay, I'm sharing here. So. Where is, okay. Yeah, so as the word here says, math repo is a mathematical research plus data repository. So yeah, folks here, yeah, put papers with code, especially code associated to papers with details on it. And here is for our paper on stage 3 models, and you can find, as I said, Macaulay to code here. So here is the code that you can copy, and here is like examples and yeah, explanations what exactly each thing means. And you can also download it here. Yeah. But you can find, by year, you can find many, so papers with code. That.
Great, thank you.
Yeah, it's kind of it's a very useful website. So we thank people that are working on it with it. Okay, so maybe so if I don't know if did any of you trying on the examples? You like one problem more or less?
You can continue with the presentation of the topic.
Okay, so we are done with this is 1 hour.
Yeah. Oh, yeah, almost
Okay,
1 hour.
so I
Yeah,
think
we can pause it.
we can finish it now. If you want, then we can continue with your lecture at 4 p.m. Is it fine?
Yeah, but I also I would like that some of you also try. That's
Okay. So if there are some questions, but people are
probably-
trying to do something, and if they will have question, might be they will ask later.
that sounds good. I'll be
Yeah.
here.
Yeah, I think so. That's the reason.
Yeah, I know. Like I believe I assumed so, but yeah. Okay.
Okay, so let's end up this session here, and we will continue at 4 p.m. Is there any question from IBA?
Yeah, there is a question.
Okay, yeah,
Okay.
sure. Please.
On a mic, okay, can you hear me, Aida?
Yes.
Okay, I wanted to ask that I read a term on that stage software, polynomial subalgebra. So does this software compute SAGB basis that is especially computed for the subalgebras? Does this software compute that as well?
The SAGB basis, I think there are packages where you can ask for the SAGB basis.
Okay.
Yes.
And it can
Macaulay
compute
do that.
Grosvenor basis?
Yes,
Grosvenor basis?
yes, you can ask Macaulay 2 for Grosvenor basis and SAGB basis.
Yeah, Macaulay 2
And
is
it may
quite
be
a
a good-
famous.
Yeah, you can. And it may be maybe even a better idea to look for SAGB bases and Grosvenor bases that are equivariant in our setting, and like when are they finite? So that's like also adds a question in our
Okay.
list. Yes, but you can do that on Macaulay 2. Yes.
Okay, thank you so much. Thanks.
Dr. Aida,
Yes.
could you please share the question with us because I didn't note all the down. So I want to try some of them.
The questions?
Yes.
The questions are on the, I think they should be on the website right now, the list of questions.
No.
They're
This-
not really. I
this
think,
PDF
either did you mention those questions during the yesterday session?
Yes.
Along the way, I think. Or you are referring to some other questions?
Was the question about the list I shared now?
Yes.
Yes. Yes.
So the
Just
list
share-
I
share
shared
the list.
now, I also sent last night, I sent an updated file that contained all the questions. I don't know if it is
Okay, maybe
if it is
we need to
updated,
check.
but
We need to check.
yeah, maybe let me double check the email, but I thought I did. If I didn't, then I'll do that right now. Let me see.
If possible, please share the updated version.
Yeah, I thought I did. That's why if I
Okay,
didn't,
it's
then
okay.
maybe yeah, I did. I have sent the new version last night. Yes. I can
Cool.
9 hours ago it says I'm gonna do reply all and start here again, and yes, I can share them also on Zoom short here, but I don't know what's the easiest way to send them. I did send them via email.
Would be
And
better by email.
I did
It
send
would be
them.
better by email to Mugi's Gas and Mugi's.
Okay, Either can
Yes.
can you resend that email because I received 2 emails from your side and 2 forwarded to.
Okay, I can send yeah, reply all. Yeah, then I apologize. I thought no, I did do that, but I maybe did not. Yeah, I did not send it to Muges. I sent it to Imran and Mariam. Okay.
The file which says here is the rest.
So the file contains at the end tutorials. The questions. Did you receive it now?
Yeah, I think
It may need a second, but
मुझे file show नहीं हो रही.
forward. Okay.
Okay, thank you. Thank you. If there is no question, so let's thank the speaker.
oh, and
Yeah, sure.
yeah, yeah. Oh, thank you. Something I was thinking, somebody asked yesterday about flag complexes, and I looked at the definition, and the definition, so according to that definition, if I'm not wrong, so the first cycle is a flag complex,
Yes.
and then the fourth cycle is not even reducible. So flag complexes are they are way more general.
Yes, because 3 cycle is non-flag, but it is not non-reducible.
Yes.
But 4 cycle is flag, but
Yeah,
it
they are
is
extremely different.
different. Yes.
Yes.
Yes, that's true.
But and the other one that was about something about the tree, I forgot the word.
Maybe you.
Yeah, it was
Decomposed-
about quasi-forest.
Yeah,
I know,
quasi-forest.
yeah, quasi-forests are decomposable in your sense, but
Yes, that's what I saw.
moment my claim about that they are the same simplicial complexes. I can't prove the other side. I mean, I can't prove that every decomposable complex, simplicial complex, as you define it, is exactly a quasi-forest. But the converse is true. Quasi-forests are decomposable, at least.
Oh, then the other, I think it is true by, so if you look at, as I said, Dobra's paper at the end in the appendix, he does a proof that like looks very similar to, they are proving that it is a quasi-forest.
Okay.
Like, yeah, so I think we went on opposite directions. So I think they just somehow, I think they end up being the same. But yeah, because the proof of that theorem that I mentioned relies a lot in this ordering in that form that like really kind of looks the definition of a quasi-forest. And yeah, Dobra's paper in the appendix, it's exactly doing that kind of yeah, rewriting the decomposable as a quasi-forest.
At the moment, I can show that quasi-forests are decomposable, but maybe
Yeah.
if you have the converse of this statement, it would be interesting.
I think the converse is like it's exactly what they write there, as I say in that paper.
Okay.
So yeah. Okay, then maybe we have the break.